Okay, let's get started. So today we're going to talk about factorization of polynomials. So we're going to get a bunch of results today that tell you whether or not your polynomial factors over the coefficients that you're working with. And I decided to cut out the proofs for some of these tests because they're quite long and I don't think they're super illuminating. So I'll point out when that is, and the proofs are in the textbook, so you can have a look there too. And so we'll focus more today on examples than on the proofs. Bean. Okay, so let me give a definition. So let's let D be an integral domain. Then so we'll take a polynomial, and we don't want it to be 0 or a unit, so a non-zero, non-unit polynomial f of x from the ring of polynomials with coefficients in D over with variable x. So we'll say f is irreducible over D. We'll see why the coefficients matter. If anytime you write f as a product of two polynomials, then either G or H is a unit in dx. Otherwise, f is called reducible. Okay, are there questions about the statement? So let me just remark that if D is a field, then this is equivalent to saying that we cannot write f as a product of two polynomials of lower degree. So if D is a field, this is equivalent to saying f cannot be written as a product of polynomials of lower degree. Okay, does it make sense? Okay, so I'm going to give you a bunch of examples to think about, and then we'll discuss them. So I'll just start writing these, and you can start thinking about them. So I'll tell you what the polynomial is and what coefficients we're thinking of it having, and you tell me whether or not it's reducible. So irreducible or reducible. So the first one is 2x squared minus 4 over the rational numbers. I'll just keep writing these. I have like 7 of them, so if you want to start thinking about it while I write, that's good. Okay, should we talk about the answers and why these are irreducible or reducible? So, what is the first one? Irreducible or reducible? Any opinion? Yeah. Why? Okay, yeah, so let's consider this factorization. So if we pulled out a 2, okay, so this is one way to factor the polynomial, but one of these factors is a unit in the ring. So this is not like I don't know what to say. This is not like a factorization of this polynomial over this ring. But what does this say about this question? So that says that it is reducible over z. Right? This factorization tells us that. Okay, so what about over q? Yeah, no, okay, so it's irreducible. And so why is that? So since the coefficients are over a field, we would need to factor it into a product of polynomials of smaller degree. So in this case, that would be 2 polynomials of degree 1. But in order for that to happen, we would need this polynomial to have its roots over q, which it doesn't because square root of 2 is not an element of q. So this one is irreducible. Does that make sense? So roughly this is because the root 2 is not in q. Okay, what about over r? Is it reducible or irreducible? Yeah. Yeah, so we can write it like this. So that makes it reducible. Okay, so then what about these next examples? What about x squared plus 1 over r versus c? So this one's kind of similar. So the roots of x squared plus 1, of course, is I, and since that doesn't exist over r, it's going to be irreducible over r, but reducible over c. Since we can write it as x minus I times x plus I. Okay, then what about for these last two? Is x squared plus 1 irreducible or reducible over z3? Yeah.
Irreducible?
Yeah, why?
Well, we need, like, if we wanted to factor into 2 polynomials of lower degree, we need the last term to be like a 2 in each to get to like 4. So we mod 3 to get 1.
Okay.
Or I guess that's like one scenario.
Yeah. Yeah, okay, so this is irreducible. So let's see why. If we did factor this, so let's say we factored it as like x minus b, x minus a, x minus b. That would mean that a and b are roots of this polynomial. So we can, since this field is small, we can just check the 3 options to see if any of them are roots. So if we plug in 0 into here, then we get 1, so that's not a root. If we plug in 1, we get 2, so that's not a root. And if we plug in 2, then we get 1, again, mod 3, so that's not a root, and so it's not possible to factor it because you don't have the roots in the field. Does that make sense? So you can use similar reasoning for this example to factor it as x plus 2 times x plus 3 over z mod 5. So it is reducible. Okay, are there any questions? Yeah.
For the 2x squared minus 4 over r, isn't 2 a unit?
Yeah, so, but we do have like this, like proper factorization.
Okay, so we can ignore like a constant.
Yeah, so we could just put this, lump that in with one of these factors. Yeah. Other question?
Wait, why for the second bullet point can we reduce it into something that isn't two polynomials of the lower degree?
For this one?
Yeah.
Because z isn't a field. So if you go back to our definition, we wanted that that whenever you factor it, you get that one of these factors is a unit. But here, 2 is not a unit in z. It doesn't have a multiplicative inverse. So this is like a good factorization for this polynomial over z. Yeah. Okay, other questions about these examples? Okay, so let's prove kind of the theorem that I was implicitly using in carrying out these examples. So this is one way to detect if a polynomial is reducible or irreducible in the case that the polynomial has small degree and you're working over a field. So let's let f be a field, and we'll let the degree of our polynomial f be 2 or 3. Then f of x is reducible if and only if f of x has a 0 in f. Okay, so I'm going to give you all a few minutes to think about this proof, and then we will discuss it. Okay, let's go ahead and prove this. So one of the directions is easy. Which one is it? Yeah. Yeah, so how does this go?
If it has a root a, then by the theorem's not x minus a is a factor of f.
Yeah, exactly. So, okay, so if a is a root, then x minus a is a factor. And then we showed this last time. So that means that you can factor your polynomial as x minus a times something else. Okay, then for the other direction, so let's suppose that f is reducible. Then we can write f of x as h of x times g of x, where these are both polynomials of lower degree. And also by last time we proved that the degree of f is equal to the degree of h plus the degree of g. And then since the degree of f is 2 or 3, that means that at least one of these has degree 1. Okay, so let's suppose h is the one with degree 1. So that means that we can write h of x as ax plus b. And then let's show that the root of h exists. So this happens when ax plus b is 0. So that would mean that x needs to be minus b over a. And this is something that we can write because our coefficients are assumed to be over a field. So I'm allowed to divide by a. So that means that this element, minus b over a, is a root of my function f over the field, capital F. Does that make sense? Are there questions? Yeah.
Why is degree of f 2?
That was just an assumption of the theorem. Here, yeah. Good. Other questions? Okay, so this theorem is particularly helpful over a finite field. Because then you can just check all of the possibilities. And then you'll know whether or not your polynomial is reducible or irreducible. And then I wanted to give an example to illustrate why we needed to assume in this theorem that the degree of your polynomial is 2 or 3. So I'll give you a degree 4 example where it doesn't have roots over the field, but it's still reducible. So here's the example. So in QX, we'll look at the polynomial x squared plus 1 squared. So this is reducible just by the way that I've written it, but it has no roots over Q. Okay. Other questions? Okay, so let's see a few more tests for irreducibility. So in general, it's hard to determine whether a polynomial is reducible or irreducible. But there are some special cases where we can say something. So let me give you a theorem called the mod P test. So this says we'll let P be a prime, and suppose we have a polynomial with integer coefficients, and suppose the degree of f is greater than or equal to 1. Then I'm going to let f bar of x be the polynomial in Z mod P obtained by just reducing the coefficients of f mod P. Okay, does it make sense? So you just take your polynomial f and you look at each coefficient and mod by p, and then that gives you the polynomial f bar. Then if f bar is irreducible, and the degree of f bar is equal to the degree of f, then f is irreducible over Q. Okay, so this is helpful because a lot of times you can, it's easier to determine if a polynomial is reducible or irreducible over Z mod P, for example, by using the previous theorem. And so sometimes you can determine irreducibility more easily over Z mod P, and then that will give you irreducibility over Q as well. And we'll do some examples of this in a moment. Yeah, do you have a question?
When are the degrees not equal?
What?
What's an example when the degrees would not be equal?
So if you modded by a prime that divided the leading coefficient, then the degrees wouldn't be equal, yeah. So yeah, so basically, yeah, what does this mean? When you're applying this test, you have to pick a prime that doesn't divide the leading coefficient. Okay, so I decided not to go over the proof of this because it relies on some lemmas that are quite lengthy in the textbook. And originally I was going to cover them, but I think I'd prefer to just get further with the course material. And if you want to read the proofs, you can find them in the book. Okay, so let me give you one more irreducibility test, and then we'll do a bunch of examples. So the second test is called Eisenstein's criterion. And it says the following. So we'll let f of x be a sub n, x to the n, and so on up to a1x plus a0. And we're going to assume that this has integer coefficients as well. By the way, both of these say something about irreducibility over the rationals, but if you had a polynomial with rational coefficients, you could always just multiply by whatever the least common multiple of the denominators of the coefficients is, and then that would give you a polynomial with integer coefficients. So these tests will work for any rational polynomial. Okay, so this is our f. Then if there is a prime p such that the following conditions hold, so p does not divide the leading coefficient, p divides all other coefficients, and p squared does not divide the constant term, then f is irreducible over q. Okay, is the statement clear? Yeah.
Is A not considered a coefficient or not?
Yeah. Other questions? Okay, so I'm going to give you time to think about a bunch of examples and then we'll talk about them. So for this, you're going to determine which polynomials are irreducible over Q. Yeah. If it's irreducible over Q, then or well, which one? Both.
Oh, I guess you're right. So like, if you don't have P, does that mean it's not irreducible?
No. Yeah. So you're looking at like 2 or 4, something. Yeah, so it could be irreducible with no prime. Yeah. Okay, so should we go through these? Which of them are easy to figure out? Yeah.
The first, the third, and the fifth.
Yeah, so why?
For the first, you can choose P equals 5, and the other two you can choose P equals 3,
Yeah.
and then use Eisenstein's criteria.
Yeah, so for all 3 of these, it's pretty easy to just like eyeball the polynomial and see if there's going to be a prime that works for Eisenstein's, and then you can like quickly decide if it's irreducible. So for all 3 of these, they're irreducible by Eisenstein's criterion. Okay, and then let's look more closely at the other 2. So let's look at this polynomial. Okay, so did anyone find a way to determine if this was irreducible? So I'm going to start by going, I'm going to try to use the mod P test, and I'm just going to start with P equals 2 because that's like the smallest field. So it's going to be easier to like, check roots by hand or something. So let's go mod 2. So that gets us x cubed plus x squared plus 1 as a polynomial. Wait, did we? I was wondering if we had already checked this for some reason. Okay, so now we can apply the earlier theorem, right? So we can just check the roots because we have a polynomial of degree 3. So I'm just going to check for roots in the field. So, oh no, 0 and 1 are not roots. So that's bad. So that means I learned nothing from doing mod 2 reducibility. Okay, so we can't do mod 3, right? Because that would kill the first coefficient. So let's go mod 5. So that gets me x cubed minus 3 mod 5 is 2. And then 9, that's 4. Okay, so now we can check. Check the elements of z mod 5. So we get 0, 1, 2, 3, and 4. Okay, so let's plug these in. Okay, so 0 doesn't work. 1 would give us 1 plus 2, which is 3, plus 2, which is 5, plus 4, so that doesn't work. Okay, so then what does 2 get us? 8, which is 3, plus another 3, plus 4, plus 4. Okay, this is also not 0 mod 5. I'm starting to get nervous. Okay, so plugging in 3, this is 2, this is 2, this is 1, and this is 4. Oh no, this also doesn't work. What? This one? Wait. Oh, this should be. So wait, this was plugging in 3. We had 9 times 2 is 18. Oh yeah. Oh, okay, great, it does work. I was like, this isn't working out. Okay, so this is 0. So what does this tell us? This polynomial has a root. So 3 is a root mod 5. So that means that the polynomial is reducible mod 5. So then by the mod p test, it is reducible. Wait. No, that's not what am I getting this like all backwards? So mod 2, we saw that it had no roots, which means that it's irreducible. So we should have already been able to conclude that the polynomial was irreducible, right? Okay, so this whole thing was unnecessary. Do you guys agree with me? So this test, so let's like go back to the statement of the mod p test. Okay, so you reduce your polynomial mod p, and then if it is irreducible, then your original polynomial is irreducible. When is it irreducible? If you check all the things and you find no roots. So this test finishes if I find no roots mod p. So we were already good just by looking mod 2. Okay, good. I had written in my notes that it worked with z mod 2, and so that's why I was like kind of surprised when we started going mod 5. I was like, what did I do wrong? Okay, does this make sense? Okay, so quickly for the last one, did anyone figure out a way to do this one, x to the 4th plus x plus 1? Yeah. Yeah. So what did you check, mod 2?
It's the same mod 2, and then you just check 0 and 1, and neither of those are roots.
Yeah, good. Okay, so if we look mod 2, 0 and 1 are not roots, so it's irreducible. Okay, good. So I think that's a good stopping point for today. So Friday we'll see a little bit why we actually care why polynomials are reducible or irreducible. Let me make one comment. So I announced this on Canvas, but the logistics of the midterm are that on Friday, we won't have office hours because there's no problem set and you're going to start the midterm. So on Friday, immediately after class, I'll post the midterm on the Canvas site and on Gradescope. So you can like download you can see the questions there, and then you will have to upload it into Gradescope by the time that it is due. Other questions about that? Yeah.
And it's open note?
Yeah, and it's open note.
And what's the collaboration?
There's no collaboration. Yeah, so hopefully it makes it clear. The front of the exam like lays out some rules, and hopefully that makes it clear what it is. But yeah, and you can only use the internet to access course materials. So the Canvas site, the textbook, your problem sets if they're an overleaf, etc. But like no like Googling. Yeah. Hey. What? No, come here.
I'll tell you in a minute. I can't say anything because the previous teacher, it's their dog. So, but the answer would be yes, I guess. Yeah. 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 I actually should go because I need to get things set up. We're finishing sympathetic low answer, Cameron Awkward Ridge. Yeah. Thank you. Thank you. Okay, bye. How are you?
Good, how are you?
I'm okay. We're almost there.
Almost.
Not quite, but almost.
Have a good rest of your day.
Thanks, you too.
You'll remember you belong to the left, to the left. Can't you see I'm the only one above you? What a way to treat the king that loves you?